So we're done taking a look at the three-dimensional Cartesian plane overall and the different coordinate systems. So now we're going to move into another segment of the course. We're going to start talking about these animals called vector-valued functions. A vector function is essentially going to be a parameterized function. Usually we use the parameter t to be able to govern that function. And essentially it just assigns a vector to each element over its domain D. So it's basically like a vector path. All right, so R is going to be our vector value function, and we usually write vector functions as R of t, and R is always going to be a vector. Most of the time I'm just going to write R of t just to understand that it is indeed a vector. And we're just going to write it as R of t is equal to a function of ti plus a function of tj on a plane, and R of t is going to be three functions in space, f, g, and h of t, multiplied by I, j, k respectively. Before, we only had, in front of I and j and k, we only had numbers. We didn't necessarily have parameters. So now we're starting to get into the fact that we could have functions in front of these unit vectors. So we're going to see how that's going to try to work with all the different types of shapes that we're going to get. First of all, we have to be able to plot, and we have to understand the different domains of these before we can start talking about calculus function. And when you talk about a domain of a vector function, it's basically going to be the domain of each of the functions that comprise the vector value function. So we just intersect all of those, and we can go ahead and from there to be able to see what this looks like for the domain. All right. And I did find a website that was really nice to be able to plot vector value functions and to see what their orientation looks like. I'm going to show you that in a separate video. But for right now, let's just take a look and be able to find the domains, and then we can eliminate the parameters. So the first one that we have is this function ti plus t plus 2j minus sine t, and that should be a k. I do apologize. I'll fix this on your version, and this should probably be bold, or not bold, and the I should probably be bold. All right, so regardless of typos, what we're going to do is we're going to find the domain of the first function, which is t. We're going to find the domain of t plus 2, and then we're going to find the domain of minus sine t. All right, so the domain of t is all real numbers, because we can plug in any number we want for t and get an output for that. Similarly, for t plus 2, the domain is all real numbers as well. All right. In fact, both of those are just lines that run infinitesimally in 2 dimensions. And then finally, for sine t, or negative sine t in this case, the domain of sine is all real numbers, and so is negative sine. All right. Remember, negative sine, you just flip whatever the coordinate is. So instead of, you'd still get the sine wave, it just flips around. All right. So the domain of R of t is the intersection of all three of those domains, and so the domain of R of t is going to be all real numbers. All right, so that one was pretty easy, just to give you an overview as to how to do this, but you just consider each of them, and when I say them, I mean the coefficients of the I, j, and k, and you just find the domains of each of those. Now, not every vector function is going to have all real numbers. So we have ln of t, we have 1 over t minus 1, and then we have e to the t, and we're going to consider the domain of each of those. So go back to pre-calculus, and remember that the domain of ln function is anything bigger than 0. The domain of 1 over t minus 1 can be any real number, except that t cannot be equal to 1, because if you do, you would divide by 0. And then for the exponential function, all real numbers. So we're just going to kind of make a big old domain sandwich out of this, and we're going to make an interval. Okay, so the domain of R of t is going to be from 0 to 1, exclusive of 0, exclusive of 1, union 1 to infinity. All right. And I will ask that you always write the interval for domains, just because that's the most common notation. All right. Another idea is that if I give you a vector value function, you should be able to plot it. Okay. And then if it's 2-dimension, you should be able to eliminate the parameter, much like you did in Calculus 2. And then if it's the 3-dimension, it might not be possible to eliminate the parameter. So we're going to use that technology that we looked at before. At the beginning, I gave you that link, and we'll use that, and I'll just show you how to work with that. So for 2-dimension, we're going to eliminate the parameter. So that's for 2D functions. And then for 3D functions, then you're just going to use technology. All right, so R of t is t over 4 plus t minus 1j. All right, so here's what we're going to do. First of all, we're going to figure out what the elimination of the parameter looks like. So x is going to be equal to t over 4. Or in other words, 4x is equal to t. And why does that help us? Well, the y value is going to be equal to t minus 1, but we just said that t was 4x, so y is going to be equal to 4x minus 1. And we know what the graph of that looks like. All right, that's just going to be a line, slope 4, passing through 0, negative 1. All right, so if we were to approximately graph this, we'd probably get something like this. However, what we need to do is we also need to figure out the orientation. And orientation is going to be what direction does it move. And here's how we do that. I'm just going to substitute two really easy values back in. T equals 0 and t equals 1. And I'm going to go back to the original, and I'm going to see what that does. Okay, so remember, we had x equals t over 4, and we have y equals t minus 1. So when t is equal to 0, 0 over 4 is 0. 0 minus 1 is negative 1. All right, so right here, 0, negative 1 is when t is equal to 0. Now, the next value that we picked was t equal 1. So let's see what happens with that. When we substitute 1 in, 1 over 4 is the x-coordinate. 1 minus 1 is 0. So we get 1/4 0, and that's going to be this point. So this is when t equals 1. And what we notice is that the vector function is moving in this direction, and that's the orientation. So whenever I ask you to graph a vector function, not only do you have to give me what the graph looks like, but you also have to plot its orientation. And the easiest way to do that is just pick two values in succession to see what the orientation is. Right? Now, not all of them are as nice as this one. All right, there are a couple sneaky ones, as is letter B. All right, so letter B is a little bit sneaky. So we have this 2 cos t, 2 sine t. All right, so here's how we're going to do this. Just like we did before, we're going to say x equals 2 cos t, y equals 2 sine t. We could divide those both by 2, and we would end up with cos t sine t. And we saw this trick in a previous video to where you can try to add the functions together after you've squared them, because you have a cos square and a sine square, which gives you that Pythagorean relationship. All right, so what you would end up with is x squared over 4 plus y squared over 4. All right, so I'm just squaring each of these right here. And then that's equal to cos square of t plus sine square of t, which is obviously 1. So we end up with this equation, x squared over 4 plus y squared over 4 is equal to 1. Right? And for those of you that might remember from pre-calculus, that's not necessarily a circle, okay, although it is a circle in this instance. It's an ellipse, but it's a special ellipse in this case. It's a circle, all right? And here's how we can figure that out. We could just multiply both sides by 4. So we would get x squared plus y squared is equal to 4. All right, so we have a circle of radius 2 at the origin. All right. And just like the previous problem, we have to determine what the orientation of this might be. All right, so to figure the orientation, let's just let t be equal to 2 values in succession. So let's let t be equal to 0, and let's let t be equal to pi halves. All right. So when t is equal to 0, remember that x is equal to 2 cos t, y is equal to 2 sin t. All right, so x equals 2 cos t, and y is equal to 2 sin t, in this case 0. And that means that x is going to be 2 and y is going to be 0. So right here, 2 comma 0 is when t is equal to 0. And so at this point, we're probably going to guess that it's either going to be clockwise or counterclockwise for the orientation, right? Unless it just stands still, which is not the case in this one. So x is going to be 2 cos pi halves, y equals 2 sin pi halves. Right. Cos of pi halves is 0. Sine of pi halves is 1. 2 times 1 is 2. So we end up with the point right about here where t is equal to pi halves. All right. Now, just because it ends up being the 90-degree angle doesn't necessarily mean that it's always going to follow that orientation. All right. So for instance, if this were negative 2 cos t, that would change the orientation. So we just kind of got lucky with this one that it follows the traditional orientation and the original angle. All right, so this is what we end up with. We just end up with a circle whose orientation is going to be counterclockwise. All right, so in the next video, I'm just going to show you how to use technology to be able to graph these 3D types of vector value functions, and then we're going to take it a step further from there.